On the vast desert worksite of the line within NEOM, construction unfolds at a scale rarely witnessed in modern civil engineering. The landscape is dominated by continuous earth-moving operations, where hydraulic excavators operate in coordinated sequences, cutting through compacted sand and fractured rock with calculated precision. Each bucket cycle is timed against the steady arrival of high-capacity dump trucks, forming an uninterrupted flow of excavation and haulage. Articulated and rigid-frame trucks move in disciplined convoys along engineered haul roads, transporting thousands of cubic meters of material every hour. Bulldozers push and spread fill layers, while motor graders refine surface tolerances to meet strict alignment requirements. Vibratory compactors follow closely behind, achieving specified density levels essential for structural stability. In parallel, drilling rigs and piling equipment prepare deep foundation zones that will support the vertical megastructure planned above ground. The operation resembles a living mechanical ecosystem. Dispatch systems coordinate fleet movement to minimize idle time and optimize fuel efficiency. Maintenance crews work continuously to sustain uptime across hundreds of machines exposed to abrasive desert conditions. Dust clouds rise beneath relentless sun, yet productivity remains constant. This is not merely a construction site. It is an orchestrated heavy equipment campaign, where excavators, trucks, and support machinery function as an integrated system shaping one of the most ambitious urban developments ever attempted. The Southern Daba Axis project marks a decisive phase in Egypt's agricultural expansion, targeting the reclamation of 16,000 acres through a fully engineered irrigation network. Delivered by Hydroelectric, the scope includes the supply, fabrication, and installation of 250 to 1,000 mm HDPE pipelines, supported by 3 high-capacity pumping stations. In parallel, 200 mm transmission lines extending 2,000 meters in Sector 12 were pressure tested using 8,000 cubic meters of water to validate hydraulic performance. Situated within the 500,000-acre Daba Axis corridor, the development forms part of the New Delta Initiative and the broader Egypt's Future Reclamation Strategy. Powered by underground reservoirs, the integrated system combines large-diameter pipelines, center pivot irrigation, 250 megawatt power generation, and a 200-kilometer internal electrical network, establishing a scalable foundation for long-term agricultural productivity. The south of El Daba Axis irrigation project marks a major milestone in Egypt's agricultural expansion strategy. Led by the Ministry of Water Resources and Irrigation, the development includes the supply, fabrication, and installation of 200 mm diameter steel and GRP pipelines forming a high-capacity irrigation backbone. Precision welding, trench preparation, pipe alignment, and hydrostatic testing are executed under strict engineering controls. Once completed, the network will deliver reliable water distribution to newly reclaimed lands, supporting large-scale cultivation and long-term regional development. The January 2022 progress update of the Kachi Canal project highlights steady advancement across multiple construction fronts. Earthwork operations continued along critical reaches, with excavation, embankment formation, and slope trimming executed to achieve specified canal geometry and hydraulic gradients. Lining activities progressed through both bed and side slopes, utilizing reinforced concrete to enhance durability, reduce seepage losses, and ensure long-term operational efficiency. Structural components of the superpassage advanced with formwork installation, reinforcement fixing, and concrete placement. Wing walls for distributary crossings were constructed to provide structural stability and controlled flow transitions. Quality control inspections and alignment verification were conducted throughout all phases to maintain design compliance. The coordinated execution of earthworks, canal lining, and hydraulic structures reflects consistent momentum toward project completion and optimized water delivery capacity. The Kachi Canal Project December 2021 progress report reflects continued momentum across multiple construction fronts. Earthmoving and canal excavation advanced steadily, with embankment formation and side slope trimming progressing as per design requirements. Reinforced concrete lining works also continued to reduce seepage and improve flow capacity. Cross-drainage structures and concrete elements saw ongoing erection and quality control checks, supported by regular alignment surveys and material testing to ensure engineering standards were met. This coordinated execution maintained the project's forward trajectory toward improved regional irrigation infrastructure. The Tizi Ouzou Highway project stands as one of the most ambitious transportation infrastructure developments in Algeria, designed to strengthen regional connectivity and modernize the national road network. Constructed by the joint venture led by Ozgan Insat, the highway forms a strategic 48-kilometer link connecting the mountainous city of Tizi Ouzou with the country's major east-west motorway corridor. The project significantly improves mobility between coastal regions and inland economic centers, while supporting long-term economic development. Engineered as a 2x3-lane motorway, the route passes through extremely challenging mountainous terrain, requiring a complex combination of tunnels, viaducts, and large-scale earthworks. Along the alignment, engineers constructed 2x21 viaducts with a combined length of 10,065 meters, along with 2x2 tunnels totaling 1,600 meters. In addition, the highway incorporates 15 underpasses and overpasses, several interchanges, and numerous culverts to ensure effective drainage and safe traffic flow at junctions and crossings. One of the most demanding aspects of the project lies in the sheer scale of earthmoving required to carve the roadway through mountainous landscapes. The construction process involves approximately 30 million cubic meters of earthworks, including 24 million cubic meters of excavation and 6 million cubic meters of fill. These operations reshape hillsides, stabilize slopes, and create the structural platform necessary for the highway's foundations and supporting infrastructure. The viaduct structures represent the most technically impressive components of the project. A total of 118 meters of viaducts in each direction are constructed using the balanced cantilever method, a sophisticated bridge building technique that allows segments to extend outward from bridge piers without requiring temporary support from below. This method is particularly suited for deep valleys and rugged terrain, where conventional scaffolding would be impractical. High-technology form travelers and precision segment casting systems are used to ensure structural accuracy and stability throughout the process. The remaining two 947 meters of viaduct structures are built using the pre-stressed beam method, a more traditional approach that employs precast or cast-in-place beams strengthened with tensioned steel cables. This technique allows engineers to efficiently construct shorter spans while maintaining high load-bearing capacity and long-term durability under heavy traffic conditions. Together, these massive bridge systems are expected to rank among Africa's most significant engineering structures in terms of total length, elevation, and span. Suspended high above valleys and steep terrain, the viaducts form dramatic elevated corridors that carry the motorway safely across landscapes that would otherwise be nearly impossible to traverse. Beyond its structural achievements, the Tizi Ouzou Highway project plays a crucial role in improving regional transportation efficiency. By providing a modern high-capacity connection between Tizi Ouzou and the national motorway network, the project reduces travel time, improves freight logistics, and strengthens economic integration between northern Algeria's coastal and inland regions. Once completed, the highway will not only represent a landmark in large-scale civil engineering, but will also stand as a transformative infrastructure corridor supporting mobility, trade, and regional development for decades to come. The Tizi Ouzou Highway Penetration Project is a 48-kilometer motorway linking the Tizi Ouzou region with the East-West Highway. Designed as a 2x3-lane highway, the route includes 21 viaducts in each direction, totaling 10,065 meters and 4 tunnels with a combined length of 600 meters. The project also features 15 overpasses and underpasses, numerous drainage culverts, and approximately 30 million cubic meters of earthworks. Major viaduct sections are constructed using the balanced cantilever method, while shorter spans use pre-stressed beams, creating some of Africa's most significant bridge structures in terms of scale and elevation. Amid the remote wilderness of northern Manitoba, along the powerful currents of the Burntwood River, the Wooskwa Team Generation project represents far more than a construction site. It stands as a milestone of engineering collaboration, advanced hydroelectric design, and a historic partnership. Construction accelerated rapidly in the spring of 2009 as crews installed extensive formwork systems and reinforcing steel in preparation for large-scale concrete placement. Reinforcing steel, commonly known as rebar, forms the structural backbone of the facility, providing the strength required for massive components such as the powerhouse foundations, intake structures, spillway, and service bay. By the completion of construction, more than 7,000 tons of reinforcing steel would be embedded throughout the generating station's structural framework. Concrete production was supported by an on-site batch plant, using aggregates excavated and processed earlier during site preparation. Transport trucks carried the freshly mixed concrete to strategic pumping locations across the construction zone. From there, powerful boom pumps delivered the material into complex wooden formwork assemblies designed to shape critical internal structures, including draft tubes, scroll cases, and reinforced foundations. Throughout the summer construction season, tens of thousands of cubic meters of concrete were placed as the core structures of the generating station gradually rose from the riverbank. A major construction milestone occurred in November 2009 with the installation of the 275-ton overhead powerhouse crane. Its massive 22.8-meter bridge beams were transported by truck to the service bay before being carefully lifted into position by heavy mobile cranes onto elevated rails high above the work floor. Technicians then installed electrical systems, motors, hoists, and control mechanisms required to place the crane into full operation. With winter temperatures in northern Manitoba frequently plunging below -40 degrees Celsius, enclosing the powerhouse became a critical priority. Structural steel framing and exterior cladding created a protected environment that allowed concrete work to continue through the harsh winter months, keeping the project on schedule ahead of turbine installation. By the spring of 2010, major progress had been achieved across the intake system, draft tubes, scroll cases, and spillway structures. Spillway gate installation advanced rapidly, preparing the facility for the eventual diversion of the Burntwood River through the structure, an essential step toward constructing the main earth dam and ultimately harnessing the river's energy for hydroelectric generation. The arrangement works of the Karata RN09 road represent a major infrastructure upgrade along one of the most challenging transportation corridors in Algeria. Executed by Ozgun Insat, the project focuses on a 7.6-kilometer section of the national road linking the provinces of Béjaïa and Sétif, specifically between the towns of Bourg-Mira and Karata. The original road, constructed by French engineers in 1865, was designed for the conditions of the 19th century and remained extremely narrow, varying between just 3.5 and 4 meters in width. The alignment presents exceptional engineering difficulties. One side of the road is bordered by steep cliffs composed of fractured rock formations, while the opposite side overlooks a deep stream valley lying approximately 30 to 50 meters below the roadway level. These natural constraints required a highly specialized design approach to safely widen and modernize the route while maintaining structural stability along the mountainside. Tunnel construction forms another key component of the project, enabling the route to pass directly through sections of dense rock while preserving the natural alignment of the corridor. One of the most distinctive engineering features is the cantilevered roadway system extending 2 to 5 meters toward the stream side. This structure uses pre-tension beams known as estacade, allowing the roadway to project outwards safely without requiring extensive excavation into the mountain. To overcome these challenges, the project incorporates a series of advanced structural solutions. Viaducts supported by reinforced concrete piers and steel beams were constructed to carry sections of the roadway across unstable terrain. Engineers also introduced innovative half-bridge structures, allowing part of the roadway to extend outward while maintaining support from the existing slope. In addition, several open-box culverts were built to manage water flow and protect the roadbed from erosion. Together, these complex engineering solutions transformed the historic RN09 corridor into a safer, wider, and more resilient transportation route while preserving its dramatic mountainous setting. The reconstruction of the Zezelj Bridge over the Danube River represents one of the most technically demanding bridge engineering operations undertaken in Serbia. Executed by AZVI, the project required a highly controlled launching process to position the massive steel arch structure while minimizing disruption to one of Europe's most important navigation corridors. The construction sequence began by lifting the steel arch using specialized climbing jacks until a sufficient elevation was reached to install sliding skids beneath the bridge deck. Once these devices were positioned, the entire weight of the structure was gradually transferred onto them. The arch was then moved forward using horizontal hydraulic jacks, allowing the massive structure to slide smoothly over Teflon surfaces that significantly reduced friction during the launching process. As the 220-meter arch advanced in cantilever over the river, a large pontoon barge was carefully positioned below the structure to support part of the load. On top of the pontoon, engineers installed a specially designed support frame composed of 4 circular steel columns, each measuring approximately 200 millimeters in diameter. These columns rested on 2 powerful steel girders, standing 2.5 meters high, distributing the loads evenly across the floating platform and ensuring structural stability during navigation. Once the load was safely transferred to the pontoon system, the slow navigation toward the central bridge pier began. This delicate maneuver relied on high-capacity winches anchored on shore, maintaining precise alignment of the structure as it moved along the river. A tugboat positioned downstream provided additional control, countering river currents and ensuring that the arch remained perfectly aligned with the final installation point. Upon reaching the central pier, the structural load was gradually transferred from the pontoon back to the permanent support using climbing jacks. The arch was then slowly lowered into its final position with millimeter-level precision. This operation required continuous monitoring and careful synchronization between hydraulic systems, navigation crews, and structural engineers. The launching operation demanded extraordinary logistical coordination. The Danube is one of Europe's primary inland shipping routes, so the construction schedule was carefully optimized to reduce the duration of navigation restrictions. The successful positioning of the 220-meter arch marked one of the most complex phases of the bridge reconstruction. Following the installation of the arch, work continued with reinforcement placement and concrete casting for the bridge deck. Temporary columns and launching beams were later dismantled once the permanent structure became self-supporting. Engineers then proceeded with the installation of the railway track connections and associated infrastructure required for the bridge's operational phase. Along the busy corridor of the Tangerang Merak toll road in Tangerang, Indonesia, engineers executed a complex operation to install massive steel box girders while keeping highway traffic flowing below. The operation required meticulous sequencing, specialized launching equipment, and carefully coordinated assembly stages to ensure safety and precision. The process began as structural components for box line C arrived on site and were organized for pre-assembly. Meanwhile, box line A underwent the primary assembly phase, where major girder segments were aligned and connected. Splice joints were prepared and coated with the primary protective paint layer to guard against corrosion before final installation. During this stage, push bars used for the launching system were assembled, allowing the girder structure to be advanced across the span. Installation components such as bearing shoes, rear rollers, and roller guide systems were then mounted beneath the girder. These elements allowed the massive steel structure to move smoothly along temporary supports during launching. At the same time, box line B components were assembled and prepared with splice coating and bolt installation, while UD1 modules were moved into position on site. With preparations completed, the girder launching phase began. Box line A was gradually pushed toward Pier P2, sliding across roller supports with controlled hydraulic force. As the structure advanced, cover splice connections were inspected and bolt joints checked to ensure structural integrity. Precision was critical, as even minor misalignment could affect the stability of the entire span. Temporary lifting towers supported the girder during positioning. Once the structure reached its final alignment, lowering towers were installed to carefully jack the girder downward onto its permanent bearings. After successful placement, bolts were tightened and inspected, confirming the final structural connections. The temporary systems were then dismantled in sequence. Push bars were removed, roller assemblies disassembled, and temporary supports taken away. Finally, the box girder was secured in its permanent position above the toll road, completing a sophisticated installation carried out without interrupting the constant movement of traffic below. At the S19 expressway construction site between Rzeszów Południe and Babica in southeastern Poland, one of the most technically demanding operations is underway: the 180-degree rotation of the massive tunnel boring machine Karpatka. After completing excavation of the first tunnel tube, the TBM must be repositioned to begin drilling the second. Engineers use a specialized air mover system with industrial air cushions placed beneath the machine, lifting its enormous weight and reducing friction with the ground. This allows the multi-thousand-ton machine to be carefully slid and rotated with centimeter-level precision inside the confined tunnel portal area before being realigned for the next excavation phase. The installation of 54-inch PVC pipeline in Burley, Idaho represents a significant phase in modern water infrastructure development across the region. The large-diameter pipeline is designed to handle high-volume water transmission, supporting irrigation networks and municipal supply systems essential to agriculture in southern Idaho. Construction crews begin with precise trench excavation and grading to establish correct alignment and bedding conditions. Each 54-inch PVC pipe section is carefully lowered into the trench using heavy lifting equipment, then aligned and joined through gasketed or restrained joints to ensure a watertight connection. Survey teams continuously verify elevation and slope tolerances to maintain hydraulic efficiency along the pipeline route. Following installation, backfilling and compaction are carried out in controlled layers to stabilize the pipe structure. Once completed, the system undergoes pressure testing and inspection, ensuring long-term durability and reliable water delivery across the agricultural landscape. The diaphragm wall construction system developed by Sambo CMC integrates advanced trench cutting, diaphragm wall grabs, and slurry treatment technology to ensure precise deep foundation excavation. The diaphragm wall grab is equipped with oil-filled, maintenance-free lifetime bearings in the pulley system, while the jaw edges are manufactured from ultra-wear-resistant Hardox 500 steel. For deeper excavation, the trench cutter employs either the hose tensioning system or hose drum system, allowing hydraulic hoses and slurry circulation lines to automatically move with the cutter during vertical operation. Excavation depth depends on the base crane capacity and boom length, while a dedicated flap control system ensures accurate deviation control during trench cutting. Complementing the excavation equipment is the high-capacity desander unit, designed to process slurry measured in cubic meters per hour. Through a sequence of vibrators, screening units, and hydrocyclones, the system effectively removes soil particles and restores slurry properties, enabling efficient reuse during diaphragm wall construction. The steel bricks assembly mock-up, carried out by Continental Engineering in Nottingham, demonstrates an innovative approach to modern structural construction. Developed as a modular steel building concept, the steel brick system is designed to accelerate assembly while maintaining the structural strength and precision associated with traditional steel frameworks. The mock-up installation provides engineers, designers, and construction teams with a full-scale demonstration of how prefabricated steel modules can be integrated efficiently into complex building structures. The steel bricks concept is based on the principle of prefabrication and modularity. Each brick consists of a precisely fabricated steel unit produced in a controlled factory environment. Structural plates, internal stiffeners, and connection points are manufactured with high accuracy using advanced cutting, welding, and finishing technologies. This off-site fabrication process ensures consistent quality while reducing the variability often encountered during on-site construction. During the mock-up assembly, the individual steel brick units are transported to the construction site where they are lifted into position using mobile cranes. Rigging teams carefully align each module according to predetermined reference points, ensuring that the structural grid remains perfectly accurate. Once positioned, the modules are connected using engineered bolted joints and welded interfaces, forming a rigid and stable structural framework. The interlocking nature of the components allows the structure to grow rapidly as additional modules are installed. A key advantage of the steel brick system is the dramatic reduction in on-site construction time. Because the majority of fabrication work is completed in the factory, site crews focus primarily on installation and connection activities. This significantly reduces labor intensity on site while improving overall construction efficiency. The modular system also allows multiple sections of a structure to be fabricated simultaneously, enabling parallel workflows that accelerate project timelines. The mock-up assembled by Content Engineering serves as a proof of concept for this construction methodology. Engineers use the prototype structure to evaluate connection tolerances, installation sequences, and structural behavior under realistic conditions. The process allows designers to confirm that alignment procedures, lifting methods, and connection systems function exactly as intended before the system is deployed in full-scale projects. Another critical benefit of the steel bricks approach lies in improved safety management. Traditional steel construction often requires extensive welding, cutting, and adjustment work at height. By contrast, the modular steel bricks units arrive largely completed, minimizing hazardous operations on site. Workers primarily perform controlled lifting and bolting procedures, reducing exposure to risks commonly associated with large structural installations. This combination of prefabricated steel assembly, on-site welding, and concrete infill allows the structure to achieve exceptional rigidity while maintaining the efficiency of modular construction. The mock-up serves as a full-scale demonstration platform where engineers evaluate installation sequences, welding procedures, and concrete placement techniques. After the steel modules are connected, Reinforcement cages are installed within designated cavities of the steel brick units. Concrete is then poured into these sections to create composite steel-concrete structural elements. The concrete infill increases compressive strength, enhances fire resistance, and improves the overall stability of the structure. Controlled vibration ensures proper compaction and bonding between steel and concrete surfaces. From a sustainability perspective, the system also offers important advantages. Precision fabrication reduces material waste, while modular construction allows structures to be modified or expanded more easily in the future. Components can be replaced or reconfigured without dismantling entire structural sections, extending the service life of the building, and improving long-term resource efficiency. Ultimately, the demonstration carried out by Content Engineering in Nottingham illustrates the growing role of prefabricated steel systems in modern architecture and engineering. As projects continue to increase in scale and complexity, modular solutions like steel bricks provide the precision, efficiency, Stretching across the historic waters of the Dardanelles, the 1915 Canal Bridge integrates advanced acoustic protection, engineered for one of the world's longest suspension bridges. Developed by Hotco, the sound barrier system lines key sections of the roadway where precision-built panels absorb and deflect the constant flow of traffic noise. Designed to endure strong coastal winds, vibration, and marine conditions, these barriers quietly perform a critical task, preserving environmental balance while vehicles surge across this monumental engineering landmark. The prefabricated basement systems developed by Berkel Fertigkeller represent a highly engineered approach to modern residential foundations. Every project begins with an individually tailored planning phase, allowing each basement structure to be designed according to the specific requirements of the homeowner and the architectural concept of the house. A fully integrated computer-assisted workflow supports the entire process, from the initial design stage through to production. Digital modeling ensures precise structural calculations and exact component dimensions before manufacturing begins. Using advanced laser technology and automated production equipment, each prefabricated concrete element is manufactured with millimeter-level accuracy, guaranteeing exceptional dimensional precision. Once delivered to the construction site, experienced installation teams assemble the basement components with efficiency and technical reliability. The system is engineered to provide maximum structural stability and complete waterproof protection, creating a secure and durable foundation for residential buildings. The company's innovative Climate basement system further enhances basement performance by offering climate-optimized construction solutions. With guaranteed water tightness and a 10-year waterproofing warranty, the system ensures long-term durability, safety, and comfort, forming the dependable foundation for future homes. At an active construction site, a grading beam paired with a tiltrotator demonstrates remarkable precision in ground preparation. Equipped with advanced hydraulic control, a tilt rotator from steel wrist allows the grading beam to rotate and tilt in multiple directions, enabling operators to shape surfaces with exceptional accuracy. Mounted on an excavator, the beam smoothly distributes and levels soil, gravel, or base material across large areas. This combination greatly improves efficiency in road construction, landscaping, and foundation preparation, delivering perfectly graded surfaces while reducing the need for repeated machine repositioning. Vacuum concrete construction represents one of the most efficient techniques for producing dense, durable concrete surfaces with superior strength and reduced drying time. The process begins with the careful placement and leveling of freshly mixed concrete across the prepared surface. Workers spread and distribute the material evenly, ensuring a consistent thickness and uniform structural base. Precision during this stage is essential, as it establishes the final geometry and quality of the slab. Once the concrete has been evenly leveled, anti-slip rings are installed at designated positions on the surface. These rings function as guides and markers that help maintain surface uniformity during the subsequent vacuum processing stages. Their placement also assists in controlling localized deformation, while excess water is removed from the concrete. The next phase introduces the vacuum mat system. Specialized vacuum mats are carefully positioned over the concrete surface and connected to powerful vacuum pumps. When activated, the system extracts surplus water and air trapped within the concrete mixture. By reducing the water-cement ratio after placement, the vacuum process significantly increases the density and compressive strength of the hardened concrete while minimizing shrinkage and surface cracking. Following the vacuum extraction stage, workers perform surface correction to eliminate uneven patches or minor irregularities that may have formed during suction. This muratory adjustment step ensures the surface remains perfectly level and structurally consistent across the entire slab. A brushing process is then carried out using wide construction brushes. This finishing technique creates a subtle textured pattern on a concrete surface, improving skid resistance and enhancing safety for pedestrians and vehicles, particularly in wet conditions. After the surface finishing is completed, the anti-slip rings are carefully removed. The removal process must be executed gently to avoid disturbing the freshly stabilized concrete surface. With all finishing steps finalized, the vacuum concrete installation is complete. The result is a high-density, smooth, and durable concrete slab capable of delivering long-term structural performance while maintaining excellent surface safety characteristics. The BOD demonstrates a breakthrough in automated construction. Using advanced 3D concrete printing, robotic systems precisely extrude layered material to form structural walls. This technology reduces construction time, material waste, and labor demands while delivering accurate, durable building components for the future of housing. A groundbreaking prototype demonstrates the 3D printing of the first 10-meter-high wind turbine base, showcasing how additive manufacturing can transform large-scale renewable energy infrastructure. Using a massive robotic printer, Layers of specially formulated concrete are deposited in precise circular patterns to build the structural base directly on site. This innovative approach removes transportation limits associated with traditional tower components and enables the construction of taller wind turbines. By allowing greater tower heights, the technology helps turbines capture stronger, more consistent winds at higher altitudes, significantly increasing power generation efficiency while reducing construction costs and material waste. The Kachi Canal project contract represents one of the major construction segments of Pakistan's large-scale irrigation development program implemented by the Water and Power Development Authority. The contract focuses on extensive earthworks, reinforced concrete canal lining, and the construction of hydraulic and transport structures along a major section of the canal system. Engineering works included more than 42 million cubic meters of excavation, filling, grading, and compaction, forming the canal prism and embankments required for stable water conveyance. In addition, approximately 919,000 cubic meters of concrete lining were installed to reduce seepage losses and improve hydraulic efficiency. The scope also incorporated key infrastructure, such as intake structures, rising mains, road bridges, village crossings, and numerous footbridge-cum-pipeline crossings that integrate local transport with the irrigation network. As part of the broader Kachi Canal system, the completed works contribute to a canal network designed to deliver irrigation water across arid regions of Balochistan, supporting large-scale agricultural expansion and regional economic development. The Egyptian Armed Forces Engineering Authority has successfully restored water flow in the Sheikh Zayed Canal beneath the Toshka Bridge, overcoming a major engineering obstacle that had halted excavation since the 1990s. Progress was delayed for decades due to a massive 9-kilometer granite mountain formation located along Branch 4 in the Toshka project area. Through intensive rock excavation and canal construction works, the 81-kilometer canal is now operational. The restored waterway plays a crucial role in Egypt's desert reclamation strategy, enabling irrigation for approximately 250,000 fedans of agricultural land and supporting long-term food security and regional development.